Okay, let's go ahead and start Chapter 1 on the topic of units and measurements. Okay, so just a quick outline of this chapter. I'll go through a quick introduction, just explaining a little bit more about what is mechanics, what is physics. Then we'll talk about physical laws and the scientific method. We'll probably stop there for this video, and then in the next video we'll do units and unit conversion, and then finally we'll have a video on significant figures, making measurements, and the corresponding uncertainty. I really encourage you to read Chapter 1. Of course, it's Chapter 1. It really does introduce the entire class, introduces the entire book as a whole, and it's a good foundation for the entire class. So I do encourage you to go through that. Okay, so just a quick introduction. What is physics? Well, physics is the study of the universe, right? Everything from the largest structures in the universe, things like galaxies, galaxy formation, things like that, to the smallest objects in the universe, things like particles and particle physics, right? Physics is an experimental science. Everything we talk about in this class is something that has been measured and observed in the world around us, and it's something that if you don't understand, you can come up with your own experiment and test it yourself, right? We all have really advanced sensors in our phones. We have accelerometers and GPS. So there's a lot we can do just at home to test physics. And then what is mechanics? What is this specific subfield of physics? Well, mechanics is a branch of physics which seeks to describe the behavior of the physical bodies around us. Things like understanding motion, forces, energy, momentum, rotation, fluids, all of that kind of comes into this giant umbrella of mechanics. A little bit more about mechanics. Why do we care about this class? Why do we care about mechanics? Well, it depends on what you're going to do in your life, but of course, mechanics forms the foundation for all of mechanical engineering, all of aeronautical engineering, all of civil engineering. So all of those careers are just mechanics all over and over again. Of course, mechanics is extremely necessary in studying robotics and biomechanics, also in things like chemical engineering and in medicine. Mechanics is extremely important for a chemist. Mechanics is really important for studying molecular bonds, understanding force, understanding energy, understanding potential energy is all critical knowledge for a chemist. Just in the world around us, mechanics can help us understand the orbit of the planets. It can explain the tides. It can explain the motion of a baseball. So when you're running to catch a baseball, your brain is kind of figuring out, where do I stand to catch that ball? That's your brain's doing mechanics. Just like the firefighters here are spraying the water. That water is following a very precise parabolic path that we can predict, right? And we'll do that in a few chapters. And finally, mechanics, it can save your life, right? Everything about a modern car is designed using just basic mechanics knowledge to produce a safe car. Things like airbags, crumple zones, seat belts, all of these objects are designed to increase the duration in which a collision occurs, and in doing so decrease the amount of force on your body, right? So if you're a engineer working for an auto company someday, you may put a force sensor in a car or on a test dummy and measure the force as a function of time acting on this test dummy during a collision or something like that. And that's something we'll seek to understand in this class. Okay, let's talk a little bit about physical laws. We'll talk a lot about the concept of physical laws in this class, things like Newton's laws, right? But we're also going to talk about modeling, the concept of modeling a lot in this class. So let's discuss those really quickly. And language can be confusing here. Within the field of science, the definition of a theory, a law, and a model have changed with time, right? But almost always in science, what we're doing is we're modeling. We're observing something in the world around us, and we're trying to describe it mathematically, right? That's modeling. We use the phrase physical law when something has been repeated many, many times. You've had many, many scientific observations, and you've always basically seen the same thing. There's no repeatable contradicting observations. So when we say physical law, it's something that, as far as we know, is true everywhere in the universe. If you went to a different galaxy and made the same measurement, it would still be true. A physical law doesn't have to always be true, though. It's true within a region of validity, meaning it's true. A lot of the things we'll discuss in this class will be true for all of your daily life, everything you observe in the world around you, they'll be true. But if you went to where I work at the Large Hadron Collider in Switzerland and you accelerate protons too close to the speed of light, a lot of this physics isn't going to work anymore. We're going to need new models. We're going to need models like special relativity, Einstein's model, to explain the physics at those extreme speeds. Right. Similarly, if you go down to the atomic level, mechanics is going to break down. So we just have to understand that what we learn in this class is true, for cars and baseballs and things in the world around us. It may not be true for a particle or for something going really, really fast. Okay. I also want to make a quick comment on the concept of simplification. Right, simplification is useful for understanding. So let's imagine we're rocket scientists, right? We're aerospace engineers. We're designing a rocket. The basic principles of launching a rocket into space are things we'll learn in this class. Things like Newton's laws and the concepts of kinematics. These are all things we're going to learn in the next month or so. Right? If we understand acceleration and velocity, we can predict and understand the trajectory of a rocket. But in reality, there's a lot of complication, right? As a rocket is flying up through the air, right, it's burning its own fuel, and its mass is drastically changing, right? So the amount of acceleration you get for a given force is actually changing because the mass of the rocket is changing as it flies, all right? That adds some complication. As the rocket gets higher and higher and higher, right, the force of gravity isn't actually constant, right? The force of gravity decreases the higher you go. You have to take that into account. And there's also air resistance. That's an added complication. And it turns out air resistance, or drag, is a very complicated force. It makes calculations much more hard because it's a non-constant force. Air resistance depends on your velocity, right? And in fact, it depends on your velocity squared for something big like a rocket. And it depends on the density of the air, which is also changing as the rocket moves up through the atmosphere. So this is an extremely complicated force, right? So to fully understand this motion, you need to include a lot of all of these different concepts in your model, right? If you're trying to simulate a rocket blasting off into space, which is why we go through the process of simplifying, right? What we want to do in this class is understand every single effect separately. Right, and then at the end of this class, hopefully we can put it all together. Right, so first we want to understand acceleration and kinematics. Then we can understand motion with a constant force. Right? If we just assume there's no friction, there's no air resistance in this magical world where you don't have to worry about those things, making that simplification is a good thing because then we can learn the most fundamental effects, and later on we can add in the other effects. Right? So try not to be put off by any simplifying assumptions. We're trying to build up and build up and build up until we have a complete understanding, right? And then in the end, if you were a real working rocket scientist, you would probably be relying on computers and simulation that would have all of these different effects built into the simulation. And hopefully those simulations would be tracking all the uncertainty that comes from any assumptions you're making along the way. Right, but if we, again, want to understand this rocket motion, well, first we can understand what happens just with the snowboarder flying up into the air. They follow this kind of parabolic path, the same parabolic path you see from this water in a fountain. Right, so we can try to understand each of these effects, and once we can predict and understand these, we can expand outwards. One other just quick thing, try to think critically and think carefully in this class. Right, don't make any assumptions. Question everything, and that's all healthy, good science, right? I'll just write a few statements down here that are all false, right? What comes up must come down, okay? That seems like it could be true. It seems like your general experience in life. You throw a ball up in the air, it comes back down. But is it always true? No, it's not, right? You can launch a rocket into space, right? If you reach escape velocity, something can leave the Earth or leave the solar system, right? We've launched satellites that are now past Pluto, right? They're leaving the solar system. Okay, what about the statement that a dropped object falls straight down? Okay, that again, from our everyday life experience, it seems true, but it's not true, right? It turns out the Earth is what we call a non-inertial reference frame. It's spinning, right? It's accelerating. So if you drop something, as the Earth spins beneath it, it's not going to appear to fall straight down from our perspective on Earth. So if you had a 100-meter deep well and you dropped a penny in it, it would not fall straight down. It would land a couple inches away from where you would think it would land, because the Earth has actually spun out from beneath it as it fell. Right? So this is something, a more complicated effect that you may learn in, for example, an intermediate mechanics class in the physics department at P&W. And finally, the statement, a vacuum sucks things towards it. That's another thing that you may think of in everyday life, but that's not true either. No, typically there's a high pressure side that's pushing on an object. All right, that's how a vacuum is going to work. So just try to think carefully, think critically, and question things in this class. Come to my office hours, ask questions, get curious, and that's all really great. So on to the next video.